Hi students, today we are going to see the technique of analog to digital filter conversion, especially impulse invariant technique. So properties of analog to digital filter conversion. So before seeing the property or analyzing the property that to be taken care while converting your analog to digital filter, we can see what is the property to be what are the properties that an analog stable filter has, and what are the properties that the digital filter have. Right, so for an analog filter to be a stable and causal, the transfer function h of s should be the rational function of s, and the coefficient of s should be real. And the second point is the poles should lie in the left half of the s plane, and the number of zeros should be less than or equal to the number of poles. So if a transfer function satisfies these 3 points, then we can say that analog transfer function or the transfer function of an analog filter is said to be stable. Then for a digital filter to be stable and causal, h of z should be a rational function of z, and coefficient of z should be real. So in this both analog and then digital, both your transfer function should be a rational function of their corresponding plane, and their coefficient should be real. The second point in your digital filter is the pole should lie inside the um, unit circle of your set plane. But in your analog filter, the pole should lie in the left half of your S plane. So if I want to convert the stable analog into a stable digital, the poles which lie in the left of the half of the S plane should be converted into inside the unit circle of the Z plane. The number of zeros should be less than or equal to number of poles. So there is nothing much different in the third property here. Right, so the property for converting an stable analog filter into a stable digital filter is the imaginary axis of S plane should be mapped to the unit circle of the Z plane. That is, most importantly, the left half of your S plane should be mapped into the interior of the unit circle of the Z plane. So whatever the technique we are going to follow, we have to make sure that the poles which lie in the left of the S plane should be mapped into the inside the unit circle of the Z. The methods of analog to digital filter conversion is popularly we will be using three different methods. One is your impulse invariant transformation, other one is bilinear transformation, the third one is approximation of derivatives. So in among these three, the first two plays a major role here. Right, so in today's class, we will see impulse invariant transformation. So impulse invariant transformation, how we are going to convert that is your analog transfer function into a digital transfer function. The basic behind this derivation will be the analog transfer function will be finding the inverse Laplace transform, so that will be getting your HA of t. And I'm going to sample this impulse response uniformly with a time interval of capital, be able to get your h of n. If I find there is a transformation of h of n, I'll be able to get your h of z. And I'll make sure that the poles which lie in the left half of your S plane of this transfer function is mapped inside the unit circle of the Z plane of this transfer function. So now let it get into the derivation here. So your h of t is nothing but the impulse response of your analog filter, and you're going to sample it uniformly for the sampling period, capital T, and your h of n will be the impulse response. So h of n will be applied if you're going to sample this one by a uniformly of a time period, and the Laplace transform the analog filter. So which you are going to consider is the h of s is nothing but your Laplace transform of your Laplace inverse transform of your h of t. And h of s is going to have an n distinct poles here. I can have a generalized transfer function as summation I equal to 1 to n ai divided by s minus pi, where pi is going to be the poles of n number of poles here. And if I take the inverse Laplace transform, So you know it very well. The inverse Laplace transform of 1 divided by s minus a is nothing but e power at into u of t. So here 1 divided by s minus pi. The Laplace transform of ha of s is nothing but ha of t. 1 divided by s minus pi is nothing but e power pi into u of t. Substitute this in the equation, what happens here, and then what I'll be getting this one. So if I'm going to sample this HA of t uniformly with a sampling period of t, I'll be replacing your t as nt. So ai e power pi, this t is replaced as nt, and u of t is nothing but your u of nt. Now I'll be taking the Z transform. So what's your Z transform? H of Z equal to summation n equal to minus infinity plus infinity h of n z power minus n. I'm going to replace your h of n value by the equation 4. Right, so h of z equal to summation n equal to minus infinity plus infinity summation I equal to 1 to n ai e power pi n t into u of t. So u of t is going to be your unit step function. So instead of this n equal to 0 minus infinity plus infinity, I'll be changing the limits of 0 to infinity here. So a here e power pi nt into z power minus n. So in this both term, I'm taking your n out. So e power pi t into z inverse. So I can write this one. You have a formula summation a n equal to 0 to infinity. A power n can be written as 1 divided by 1 minus a. So I'll be considering this as an a power n. So if it's so, h of z is equal to summation I equal to 1 to n ai 1 divided by 1 minus e power pi t into z inverse. So now if you compare this h of s and h of z, 1 divided by s minus pi is transferred to 1 divided by 1 minus e power pi t into z inverse. So if I equate these two things here, I can find the relationship between your analog poles and digital poles. That is, s is nothing but your pi. So when s minus pi is equal to 0, I can take s equal to pi. When I equate this denominator into 0, that is 1 minus e power pi t z inverse, I can get it out as z equal to e power pi t. So now replace your pi as s here, right? So I can get the relationship by that is equal to e power st. So I can write your z s plane as sigma plus j omega, where just omega is nothing but your analog frequency, and e power a plus b can be written as e power a into e power b. Now, Z plane can be written as R into e power j omega, where R is nothing but your real and this omega is nothing but your digital frequency. So I can write it out as R e power j omega, which is equal to e power sigma t e power minus j omega t. Equate your real and imaginary part. So Z is equal, that is your R equal to e power sigma t, and Z is equal to j omega, sorry, omega t. Now the mapping, after the mapping is done, we have to see that the condition of converting your analog to digital filter has been satisfied. That is, left half of your S plane has been mapped into the inside the unit circle of your Z plane here, right? So suppose if your alpha or sigma is going to be less than 0 here. So suppose if you take your sigma is equal to minus 5. So if it is sigma is minus 5, then what will be your R value? So e power minus 5. So definitely the value is less than that of your 1. So take your calculator and then find out, put it in your radiant mode and find it out e power minus 5. So the value will be less than 1 here, right? So what happens, the modulus of z is going to be less than 1. So it lies inside the unit circle. Suppose if your sigma is equal to 0, e power 0 is going to be 1. It lies exactly at your unit circle. And if your sigma is greater than 0, you can take it as a, suppose sigma is equal to 10, then e power 10 is going to be greater than 1 here. So which lies outside the unit circle. Suppose if this is going to be your S plane here, and this is your real axis, and this is going to be your imaginary. So what happens? This is going to be the left half of your S plane. This is going to be your right half of your S plane. If it's so, what happens? All your left half of your S plane is mapped inside the unit circle of your unit Z plane, because the value will be definitely less than 1. And for exactly at 0, the value will be exactly 1 here. And for right half of your S plane, your modulus of Z is going to be greater than 1. So it is outside the unit circle. So then from this one, we can say that the impulse invariant technique will convert the stable analog filter into a stable digital filter. Let us solve a problem here. Before that one, you have three formulas in your impulse invariant technique. So the H of S, what they have given in your question, should be converted into any one of these three forms. One is your 1 divided by S minus P. The formula is 1 divided by S, 1 minus e power P I T into Z inverse. So if I substitute this formula in this formula, my H of S will be converted into your H of Z. So if your H of S is the denominator of your H of S is factorizable, then probably it fell into this equation here. So this is for of second order or third order here. So S plus the second formula is S plus A divided by S plus A whole square plus B square means 1 minus e power at cos bt z inverse divided by 1 minus 2 e power minus at cos bt z inverse plus e power minus 2 at z power minus 2. And next is b divided by s plus a whole square plus b square is equal to e power minus at sin bt z inverse divided by 1 minus 2a power at cos bt z inverse plus 2 e power plus e power 2at z power minus 2. So in this form, both your denominators are same, only the numerator is going to be different. So while you're reading the problem statement, after seeing your H of S, if your H of S denominator is factorizable, then it will fit into this formula here. Right? Suppose if your H of S, denominator of your H of S is not capable of factorizing things here, then it will fit into either this formula or this formula. Then what happens? You have to check in the numerator. If your numerator has your variable S, then it might fit into your S plus A divided by S plus A whole square plus B square. Suppose if your numerator is going to have only constant, then it will fit into the formula B divided by S plus A whole square plus B square. But your calculator should be in gradient mode for this impulse invariant technique. So keep your calculator in gradient mode and compound mode. First problem, for the analog transfer function h of s equal to 2 divided by x square plus 3s plus 2, determine h of z using impulse invariant transformation for t equal to 0.1 second. So here, after reading this problem statement, you have to get two things here: your h of s and what technique they ask you to convert. Right. So here, impulse invariant technique. So immediately take your calculator and put it in your radian mode compound mode. So take your h of s, and first, before start doing the things here, first write what are all the things given in the statement. So h of s equal to 2 divided by s plus s square plus 3s plus 2, and factorize your denominator. You just see to that whether your denominator can be factorized or not. So you can use your formula method, or you can use your calculator to find the factors here. So how to find the roots of the equation using your calculator? Take your calculator, press your mode here. In that mode, you'll be having your fourth time. If you press, you'll have your mode called equation, EQU. So you just press that one, and upper you'll be having a side arrow. If you press that one, what happens? If you press your equation, you'll have your unknowns here, right? So if you press your side arrow, you'll be getting your degree here. In that one, choose your, it's a second order, so you just use your second order degree. So now what happens? It will blink out A equal to what? Now you just substitute that as 1, as your first value will be A. Here this can be written as A square plus BS plus C. And if you press your 1 and equal to, next it will display it as B equal to what? Now press your 3, then equal to. Now if you check, you'll get your C equal to what? Now press your 2. Now if you press your equal to, you'll get x1 is equal to 1 value, and if you press equal to again, x2 equal to as a minus 2. So you can factorize your h of s as 2 divided by s plus 1 into s plus 2. So since it is factorized, you are able to factorize, it will fit into a first formula here. So after for that one, it should be in the sum term, but here it is a product term. So I'll be using a partial fraction method to convert it into a sum term. So since you have two terms in the denominator, I'll be needing two constants. So a divided by s plus 1 plus b divided by s plus 2. So now I can write this one as equate this h of s as 2 divided by s plus 1 into s plus 2, and LCM you can cancel this one, so that I can have equal to a into s plus 1 plus b into s plus 2. Sorry. So it will be of a into s plus 2 plus b into s plus 1 equal to 2. Substitute your s as minus 2, I'll be getting your b as minus 2. So if I replace it, I'll get your h of s as 2 divided by s plus 1 minus 2 divided by s plus 2. Then by impulse invariant, so this will fit into a 1 divided by s plus pi, and here it is 1 divided, that is your 1 divided by s plus pi. So 2 divided by 1 minus e power minus t is z power minus 1 minus 2 divided by 1 minus e power minus pi t into z power minus 1. Here they ask you to substitute your t as 0.1. Suppose if they didn't give any, if they didn't mention anything about your t, the t value will be 1 second. Right, so replace your t as 1 second now. So now h of z 0.1 second. So h of z equal to 1 2 divided by 1 minus e power minus 0.1 into z power minus 1, and 2 divided by 1 minus e power minus 0.2 z power minus 2. Use your calculator. So 2 divided by 1 minus e power minus 0.1. So calculator should be in radian mode. So it's minus 0.9048 z inverse. Find the value of e power minus 0.2. It's 0.8187 z power minus 1. I always recommend you to take after your decimal, 4 places after your decimal here. Right, so if they ask this question in terms of your 2 marks, you can stop here. If they are going to ask it for 4 marks or 6 marks, you have to find your h of z such that the denominator of your h of z should start with 1. So I'll be taking your LCM and then cross multiplying here, and then I'll be simplifying. I'll be multiplying the entire term. So this a minus b into c minus d, I'll be getting this value, and here also I'll be multiplying this 2 and removing the bracket here. Then your h of z is equal to this plus 2 minus 2 get cancels. H of z will be of 0.1722 z inverse divided by 1 minus 1.7235 z inverse plus 0.7408 z power minus 2. So now my h of s has been converted into a h of z. So we'll go for another one problem here. So convert the analog filter with the transfer function h of s equal to s plus 0.1 divided by s plus 0.1 whole square plus 9 into a digital filter using impulse invariant transformation. Here it's very simple. By seeing the h of s, we can guess what formula it will fit. So s plus a divided by s plus a whole square plus b square. Normally students will make a mistake here. They'll be taking your b as 3. So you have to take it out as a 3 square. So your b as 3 here. Right, so this is the formula here. So a value is 0.1 and b value is 3. So I'll be substituting my a value and b value, and here they didn't give anything about your t, so I'll be making use of my t as 1 here. Right, so there's 1 minus e power minus 0.1 t cos 3t z inverse divided by 1 minus 2 e power minus 0.1 t cos 3t z inverse plus e power minus 0.2 t into z power minus 2. So here I have replaced only a and b as 0.1 and 3. Now I am assuming t equal to 1 sec. And then if I substitute the values here, I'll be getting this one. So it's very easy to get your things here, right? So I'll be saying one more problem. Convert the analog filter with the transfer function h of s equal to 1 divided by s square plus 0.5 s plus a digital filter using your impulse invariant transformation. So here we can see that the denominator of your h of s cannot be factorized here. So what happens, obviously the h of s will fit into any one of s plus a divided by s plus a whole square plus b square, or b divided by s plus a whole square plus b square. But here in the numerator we don't have any s. So obviously it will fit into b divided by s plus a whole square plus b square. And you know the formula here. Right, so now I have the function of s square plus 0.5 s plus 2. I don't know the value of your a and b here. So without knowing your a and b, I cannot fit into this formula here. So my aim is to make you my h of s, that is the h of s that is given in the problem statement, to fit into the form b divided by s plus a whole square plus b square. Now I can equate the denominators. So s plus s square plus 0.5 s plus 2 should be written in terms of s plus a whole square plus b square. Now I can expand this s plus a whole square plus b square as s square plus 2as plus b, as you have the formula a plus b whole square. And then I'm just equating the coefficient of s. So 2a equal to 0.5. So from this one, I can identify your a as 0.25. Now I'm going to equate the constant. So a square plus b square equal to b square is nothing but 2 minus a square. I know the value of a, which is nothing but 0.25. So my b square value is 1.9375. So to find the value of b, I'll be replacing it at 1.3919. So here the second place where the students always used to do the mistake here. So here they'll be taking the b value as 1.9375. So actually you have to take the square root and then you have to take it. Now I can write this 1 plus 1 divided by s square plus 0.5 s plus 2 as 1 divided by s plus 0.25 whole square plus 1.3919 whole square. So now my h of s is this one. But I have the formula for b divided by s plus a whole square plus b square. But I have the b value is actually 1.3919. So to make that b value in the numerator without changing the value of the function, I'm just multiplying and dividing it by same value. And you know what thing here? A divided by a can be written as a into 1 by a. So likewise, I'll be taking this as 1 divided by 1.3919 into 1.3919 divided by s plus a square plus b square. Now this 1.1 divided by 1.3919 is 0.7184. And now here this one will give you the will be given by this formula. Okay, so by substituting your a value and b value as 0.2, I'll be getting the equation here. So keeping your calculator in your radian mode, and then I'll be substituting the values and getting the equation here. Now 1.3919 divided by s plus a whole square plus b square value is this one. But it should be multiplied by the constant value here. So my h of z, if I multiply it by the numerator, the h of z is equal to 0.5506. That was divided by 1 minus 0.2771 z inverse plus 0.606 by z power minus 2. So normally the third place where the students will do the mistake, they'll be entirely forgetting this constant value here, right? So to keep all these things in your mind while starting doing your problems here, you should be very conscious and you should be very concentrating while doing your problems here, right? So this is about the impulse invariant technique. So for clarifications, log on to vanilla.blogspot.com. You can meet it in a next presentation.